All right, next up we have Javier Perez, who's joining us from the Department of Epidemiology at the Johns Hopkins Bloomberg School of Public Health and the Geneva Center for Emerging Viral Diseases. He'll be speaking about the challenges and opportunities in modeling the effect of weather and climate on cholera dynamics and control.
So I'll rebound on Mr. Markawa's mentioning of rainfall in driving the outbreak to talk about challenges and opportunities in modeling cholera and climate from a more, let's say, broad perspective. So cholera and climates are topics that have been received significant attention recently. For instance, the WHO Director General mentioned that climate change was turbocharging cholera in 2022. And also in the IPCC 6 assessment, cholera is asserted to be affected by climate change with very high confidence. So this brings us to understanding a little bit better from where this evidence comes from and what's the current state of our understanding of these associations. So cholera has been proposed to be a paradigm of the effect of global climate change on infectious diseases. And this really from a microbiological and ecological perspective, because Vibrio cholera has been shown to live in natural aquatic environments, and the environmental conditions of the environments could affect cholera ecology and thus cholera epidemiology. And this has been further, let's say, supported by studies of the link between interannual variability of cholera in Bangladesh with the events of strong events of El Nino, Southern Oscillation. And this has really strengthened that idea that cholera is a strongly climate-sensitive disease. This leads us to assess in the literature current estimates of the associations between cholera and different aspects of climate and weather. And this is a systematic review that we're finalizing that is led by Chulu Zhang in the group. And from the papers we extracted, we actually found a more nuanced picture of what is published in the literature. Most evidence comes from Southeast Asia, in particular Bangladesh, which is considered the homeland of cholera. And actually, if we look at different covariates and different spatial scales, the associations are rather inconsistent. It's not a clear-cut picture of how things are related. And this is probably due to context dependence of these associations, but also possibly to heterogeneous study quality between published estimates in the literature. So this brings us to challenges in modeling the associations mechanistically between cholera and climate and weather. And this is something that is not specific to cholera, and this is a nice review that looks at water-associated diseases in general. And one of the findings is that there are really a diverse set of approaches and methods that have been used to study the relationships between weather, climates, and water-associated diseases. And there are severe challenges in terms of the epidemiological data that are used in these analyses, but also the climate and weather data. And this is further strengthened by challenges in understanding water-associated diseases that have multiple transmission pathways. Another challenge is actually the interplay between climate forcings, climate weather forcings, and the immunity dynamics of cholera. And this is a classic paper by Coel et al. That was showing that there were periods in which, due to low susceptibility because of previous infections, climate did not seem to have a strong impact because if we didn't account for immunity dynamics. But once they accounted for these, they were able to show that the changes in transmission strength could be associated to changes in discharge in the main rivers, but also flooded area. But actually, in a further analysis using similar methods, King et al. Showed that the immunity dynamics could actually be very different in Bangladesh. And you can see the two curves in the panel A, where blue is the new estimates that they were proposing, which showed the strongly varying susceptible fractions. And the red curve is using the same method as in the paper on the left. So this means that how we account for immunity can really change the way in which we understand the associations between the outcomes that are number of cases or deaths and climate signals. Another challenge that was mentioned earlier is how we think about transmission of cholera. And we can think of two extremes, one as a spillover events, a really environmental disease where cholera ecology in aquatic water bodies can change due to climate and weather. And this affects cases that we see in the community. And on the other extreme is really as a human-to-human disease, following the fecal-oral routes. And here the 5F diagrams to remind us of the complexity of these disease transmissions. And we've recently tried to argue that the way we think about transmission actually also has implications on the way we try to project the effects of climate change on cholera transmission in the future. For instance, the different environmental factors such as temperature or extreme weather events could either affect cholera ecology in water bodies, but also disrupt water sanitation infrastructure that could increase human-to-human transmission. And this probably depends strongly on the transmission pathways that are context-dependent. Another effect modifier that from the hydrological perspective is the previous hydroclimatic conditions on the effect of rainfall. And this has been formulated as a concentration dilution hypothesis by Cray et al., thinking of diarrheal diseases in general. And the idea is that dry conditions on which extreme rainfall occurs favor transmission due to the concentration of pathogens in the water. But wet previous conditions could actually lead to dilutions with extreme rainfall, which could lower the risk. And they found in a meta-analysis evidence for the concentration hypothesis, a little bit less for the dilution hypothesis. But this is just a reminder that understanding these relationships could actually be quite complex and maybe depends on climate zone, but also affect modifiers with wash infrastructure. So this brings us to the current state of mechanistic modeling of cholera and climate. And this is just to present a small scoping review of these studies. But before that, what we can think of what are the different reasons why we would be interested in modeling mechanistically cholera and climates. And these are a few, possibly for spatial targeting and interventions to offset the effects of climates and weather on cholera outbreaks. A more classic one is forecasting, thinking of early warning systems, that if we believe that cholera is a very climate sensitive disease, then we should be able maybe to predict outbreaks or case epidemiological trends within reasonable time horizons. But also more thinking about climate change studies of attributing specific outbreaks to weather, a specific weather event, or even to climate change more in general. And finally, more strategic modeling and thinking how to potentially offset the effects of climate change through interventions such as timing of vaccine campaigns. So to go into the results of the scoping review, the results cover 18 papers where mechanistic models of cholera were incorporating one form of weather and climate data. And most of the studies actually focused on rainfall. And this is a classic example or a representative example in Lemaitre et al., where rainfall is thought to increase either the exposure or contamination of bacteria. And most of these models are forced by satellite-derived rainfall. A nice example of considering nonlinear effects of rainfall is this analysis by Kamatra et al. In the Yemen epidemic in 2017, where they've been finding a nonlinear effect of rainfall which peaked around 30 millimeters, but then decreased. Another example of a little more complex model where hydroclimatic variables were modeled explicitly in terms of evapotranspiration and precipitation, which actually modified the water volume in which bacteria lived, which concentrated bacteria, increasing the strength of transmission. And this, in this study, they argued that these mechanisms could explain different seasonalities of cholera in Bangladesh in historical data. And final example showing the potential use of these type of rainfall-driven models is this study by Bertuzzo et al., where they were trying to predict the probability of the extinction of the Haitian cholera epidemic using bootstrapped estimates of rainfall patterns 5 years into the future. There were very few studies that looked at climate drivers. This is maybe the only one where they were trying to look at the effect of ENSO 7 months before on cholera outbreaks in Dhaka in Bangladesh. And previous evidence in Dhaka suggested that ENSO was a strong driver of large outbreaks. And in 2016, it was a particularly strong ENSO year, so we could have thought that there would be a large outbreak, as the model here predicted in red. But actually, the cases remain quite low in that year. which is a reminder of the difficulties of using these climate data without accounting for the mediations of local rainfall patterns or temperature fields that could affect transmission. And finally, there were very few studies using temperature directly, and this is one of them by Kopke et al. That explicitly modeled an environmental component of transmission, which is the blue line and gray areas. And actually, it was interesting because they were arguing that the environmental component was much larger than the human-to-human component, which is the red lines there. So this brings me to a few gaps that come out from the scoping review. The first one is that there are actually relatively few studies that, at least I found, that incorporate weather and climate data mechanistically in models of cholera. In terms of weather variables, there's a lot of potential work to do on rainfall in terms of lags, transformations of rainfall, the incorporation of previous conditions, so thinking of the concentration dilution hypothesis, and potentially the effect on different epidemic phases, distinguishing between the early epidemic growth and later in the epidemic. And for temperature, as I said, there are very few studies, and maybe more data-driven incorporation could look at bacterial dynamics or thinking maybe of exposure dose to incorporate temperature. For climate signals, the only example was this forecasting analysis, but I didn't seem to find any scenario modelings or strategic modelings, which is something that could be interesting. And finally, all the effect modifications with wash conditions were not explicitly studied in these studies. And neither were the effect modifications by immunity dynamics. Often in these models, the immunity compartment dynamics were either fixed or sometimes inferred jointly, but there wasn't an explicit consideration of how these joint inference could affect the signals that were extracted from the data. In terms of data gaps, many of these studies use satellite data, not in situ weather and climate data. And finally, the epidemiological data has no limitations, as is typical for cholera, of using suspected versus confirmed cases. And there are few studies that used mechanistic models for other purposes, such as strategic modeling and attribution studies. So to conclude, and for future possible works, is despite all the evidence on the associations between cholera and climates, accounting for this mechanistically is still a relatively young field. There's work to do to account for the diversity of transmission settings that are relevant today for cholera control, but also the diversity of model purposes that could be used for control purposes. There's also opportunity to combine mechanistic modeling with more epidemiological studies to disentangle transmission pathways for cholera, and also to account for effect modifications, as we mentioned earlier, and also potential use for novel epidemiological data sources along with case data such as serology, genomic data, environmental DNA, and wastewater sampling. So with that, I would like to thank you for your attention and thank the group at Hopkins, and also this work is within the Vaccine Impact Modeling Consortium and also funded by the Gates Foundation. Thank you very much.
Thank you, Javier, for a very interesting talk. We have a few moments for questions, if anyone has any to ask.
Thanks, Javier. Great talk. I was just curious, in your from the review that you've done, can you point to any locations that have not only the climate and the weather data that you look for predicting cholera, but also immunity data and your effect modifiers? Or if it's not from the reviews that you've seen, do you know of any locations that would have all of those kinds of data available that would be good places to model this?
So I'll refer to Judith's presentation earlier about Uvira and DRC, where it's maybe one of the few places outside of the Bay of Bengal where we have this type of rich data for a relatively long period of time, right? Because this is also looking at multiple seasons is important. So I think that's a unique place where we could also look at these type of questions. And then maybe more long-term surveillance data sets probably be in Bangladesh, combined with the newer serology, cross-sectional serologies that have been done in the country. is maybe an interesting place. And I think that's overall, it's important to consider different types of transmission settings, and probably Bangladesh is very different than DRC, that is very different from Nigeria. So ideally, we would try to expand as in as many places as possible. Yeah.
Hi, Alicia Cray. I just wanted to point out that the lag question is really, really difficult to deal with, in part because the actual lag between, an extreme rain event and disease is going to vary by context based on the level of wash infrastructure, so how quickly water flows through the system, and what people are using, how quickly they access that water, or if it's treated, or, how much resilience the system has. And I don't know. I think it's important to study, but I don't think we're going to get to one number just because of all of those different variables. And we actually when we did this review, we had a reviewer who told us to just pick the strongest lag for each site. And we were like, that's data fishing. Or they told us to do a distributed lag model with a specific decay rate. But there were a lot of studies that did lags at different, maybe 0 to 21 days, and the shape of the associations was different in different places, even for the same pathogen. And so I just wanted to point out that it's actually really, really complicated to try to deal with that.
Yeah. Just to comment, I think that's most of the answers to the questions will be context dependent, but hopefully we could try to partition some of that variability in things that we can either measure or understand. And probably hopefully we can, by analyzing things in different settings jointly, we could maybe get at that. But I agree that we shouldn't think that there's one lag and one effect size and of all of this.
Maybe also taking the complexity idea a little bit further, I was curious, a few of the studies, or one of the studies that you showed, I think did 5-year forecasts based on some climate data. And then there was another study looking, we've already mentioned the lags, looking at ENSO. And I'm curious, because there's a lot of data sources nowadays for different climate models that are, provide historical data, as well as that forecasted far years into the future, as well as forecasts for things like dipole mode index. And so, which are forecasted several months into the future. And so I'm curious, just based on your deep dive into the literature, your opinion on the merits versus the risks of doing longer term forecasts, seasonally or many years.
Well, I suppose it depends on what you're forecasting. Is it the number of cases? Is it probability of an exceptional outbreak? And I think this study by Martinez et al. In Dhaka is a clear example of they did 11 months, the lag of ENSO that was found in the previous modeling analysis and got it wrong. It was totally wrong. And in the discussion, they tried to understand why or explain possible hypothesis of why. But I think it's, if we really think of in terms of forecasting, the time horizon should be really an important thing to think about of what is reasonable to expect that we can do or not. For longer time horizons, then it may be, it's not forecasting that we're thinking of, but more like strategic modeling, in which is more comparing alternative strategies to offset possible changes in rainfall patterns or things like this. But that's a different type of modeling, right? So maybe that's a question of the time horizon that we choose and what's the purpose of the modeling. But for forecasting, I don't think that it will be easy to do for very long periods. Yeah.
Agreed. Thank you so much, Javier, for the talk and the comments. And please join me in thanking Javier.
Thank you very much.